Assalamu alaikum, everybody. Today we'll be covering an important topic in natural language processing, which is information retrieval. In general, we are going to be talking about information retrieval systems, as well as some of the techniques, including TF-IDF. Let's start. Let me share my screen. I hope everyone can see my screen now. So today's topic is information retrieval. This is slightly different from what you have studied in database systems or courses like that. Uh, information retrieval is the task of fulfilling an information need. See, and this need is going to be fulfilled from a collection of documents. So essentially, we have a query of sorts, and we have a bunch of documents, and we are trying to fulfill the needs of that query. So we are interested in retrieving required information from a huge collection of text documents, and that's where NLP comes in. So for example, uh, web search is a form of information retrieval. A lot of the times, these lawyers are spending huge amounts of time just searching through the previous cases to figure out, okay, which earlier cases or precedents has been established in cases similar to what they're handling right now. So legal information retrieval, etc. So the basic model of information retrieval is that you have a bunch of documents. So you have document, and you have another document, and you have a number of documents. See, and here we are considering text documents. Then what you get is an information need, which can be a question, which can be a query. So that information need is sent into the system, and the system then outputs some information that can be used for fulfilling this need, right? So IR systems were ironically built to reduce information overload. So web search and these search engines were actually built so that users are not loaded with extra information, a lot of information that confuses them. See? So the general architecture of an information retrieval system, or the flow, I should say, flow of an IR system goes this way. So there is, the user defines his or her need. So there is the user need for information, or the user, I should say, the user task. And that task that the user wants to fulfill is converted into an information need. So essentially, there is a downstream task that the user wants to perform, and for that, the user wants to fulfill an information need. That information need can perhaps be converted into a query or a question, right? or these can be search words, right? Then these are fed into a search engine. This search engine, on the other hand, has been inherently fed with a huge number of documents, right? So, for in the case of Google, it would be a general crawl of the entire web. Then this search engine would output a set of results, which might be web links. Then, if this does not really work, then there is this step of query refinement, because eventually we want to fulfill the information need that can be used for the task. If the results are not uh, substantial or useful, then this query is refined and again fed into the system. So this loop continues until the information need is fulfilled. Right? So as an example, you can think of the user task of how to, let's say, the user wants to treat COVID, right? And then, so he or she has a need of trying to figure out information. Ki how can I treat COVID, whether through traditional mechanisms? So they would search. So there is this need. So the need is info about COVID treatment. And then the user formalizes this by, so there is this search, the Google search bar, and he adds COVID 19 treatment using. And if you put using, you will see a huge list of things: using baking powder, using uh, radiotherapy, and so forth. So a lot of using AI perhaps or artificial intelligence. So you'll see the Google search engine gives you these weird kind of options when you are trying to fulfill your information need to execute a task. So the problem now is that now we reformulate the problem of information retrieval. Okay, we have a bunch of documents. We have these documents, and we now have a query, whether it's a combination of words or whether it's a formulated query, whether it's a question. So given a query and a document, is document X relevant? One. And two, which documents are most relevant? So that's ranking. How would you rank? And this is the one of the most important things that Google solved from the very beginning. That how can you rank different web pages in order of relevance? So the solutions are numerous. So we'll start with the simple solution, solution A. We formulate the solution as such. Do query words occur in the document? Right? And this brings us to binary term document incidence matrix. So this is what the matrix look like. So you have terms, let's say term 1, term 2, term 3, all the way to term n. So you have listed all possible terms that can occur in queries. Then you have documents, document 1, document 2, document m. And then you have uh, this matrix. So if term 1 occurs in document 1, you have a 1. If term 1 does not occur in document 2, it's a 0, and so forth. Right? Term 2 occurs in document 1, does not, then it's a 0. It occurs in document 2, yes, it occurs in document M, it's a 1. So same thing for term 3 all the way to terms. These terms might just be keywords, right? So something like that. So you have a binary term document incidence matrix. So this is what that matrix looks like. Right? How are we going to search through this matrix, and which of the above questions is it going to answer? So given a query, is document X related? You go to the document, you look at the term. Okay, given a term, let's say it's term 3 and it's document 2. No. So this document is not relevant given this term. See, which documents are most relevant? You look at the term, let's say it's term 3. So document 1 is relevant and M is relevant, but it does not tell you how to order these documents. It just tells you that this term occurs in these documents. See? And that brings us to the second solution, which is how many times the query words occur in a document. See? So you can simply think of it as an extension of the binary term document incidence matrix as a term document count matrix. See? So you have a similar matrix. You have terms, term 1, term 2, all the way to term n, and you have the documents, document 1, document 2, all the way to document m. Okay. And you count. If term 1 occurs 2 times in document 1, it's a 2. It does not appear in document 2, then it's 0. If term 1 occurs, let's say 25 times in document n, then that would be 25. So essentially, instead of keeping the binary matrix, we keep a frequency matrix. So it might be see, so this would be this is called uh, term document count matrix. See? So that brings us to solution C. The next question is, where in the document do the words occur? Words appear. So the thing is, if words appear early in the document, so let's say you have this document and you have a query. So the query has these words. So where do these words appear? Do they appear towards the beginning of the document, towards the end of the document, or somewhere in the middle? Because it does really matter. If terms appear in the beginning of the document, that means that this document is relevant to these terms, see, or these query words. Now, the more difficult question is to solve how important is the query word. Should we be even searching for this query word in the document? Because there's some words called stop words. So in the query, for example, you have the treatment for COVID. See? Now in this query, the word the does not really add anything. Neither does for. So these are actually stop words. Right? So they're not really adding anything to the query except for making the sentence grammatically correct, which is not necessary uh, for the query resolution or the fulfilling the information need for, in this case, for information retrieval. So now this brings us to the bag of words model, which you may have seen in some other courses. And we are looking at it purely from an NLP perspective. We are removing, if we are removing the stop words and we don't really care about the grammar, so does it even matter these words which are important are also aligned temporally? Not necessarily, maybe. And perhaps it's not really adding anything to the way we are processing queries. So that means, let's look at a few examples. So let's say there is document one that says the fox is quicker than the dog. And let's say this is document one. Then there is document two, which says the dog is quicker than the fox. Now, these two documents are giving us two different pieces of information, but in the bag of words model, the thing is we get a bag. We create a bag of words. So in the bag of words, we are removing the stop words, which are not really adding anything for us, and then putting the rest of the words in the bag. So the bag would contain fox, dog, quicker, and that's about it. So it turns out that both of these documents have the same bag of words, right? Now, if we have dog, fox, quicker, who is quicker? If we have a question like this, if we have a query that says, who is quicker, dog or fox? Then how would you say that this document is more relevant or this document is more relevant? Because it the bag of words is the same for both documents. And if you're looking at the query, you would be doing the same thing. You would be cutting out or is, and you want these keywords. And the thing is, you are going to get the same document. So we need something else. The bag of words model generally works well in many cases, but this is where I'm showing it does not really work. So we need something more. And here we want to give some sort of importance to the terms. And why would we give importance? So one of the things that I mentioned, okay, perhaps the order in which the terms are occurring matter, right? So, before we get on to that, let's look at which terms to give more importance to. And why. See? So, one of the things is that frequent terms are more important. That means that if a document uses a term multiple times, that means that this document is important for that term or regarding that term. See, barring stop words. So we are not talking about the, for, is, and so forth. So there are about 50 or so stop words, very common stop words. Other than that, if you're looking at these terms, frequency is a good measure of importance. Okay? Another measure of importance are rare terms. And this is sort of counterintuitive, but you will figure this out by the end of the lecture. Rare terms are more informative. So if terms rarely occur anywhere, so for example, uh, the term or the word anthropocentric, see, rare term rarely occurs, but anthro means something related to human beings. Po connects the centric to something that's centered around humanity. And these kind of terms should get higher weight. We are weighing terms in our matrices, so these terms should somehow get a higher weightage than some of the other terms, which might be more frequent. See? So that brings us to term frequency. We are going to tackle each one of these one by one. Term frequency and how we measure it. So term frequency is generally called TF. You may have heard of it at some point. So this is the raw count of a term in a document. Okay. So basically, you count the number of times a term occurs in the document, and you give it out. So you can call it the frequency term document. See? So you, this would be TF given a term and a document. So let me give you an example. Let's say you have a term oysters, and you have a document oysters eat oysters eat oysters. Okay, let's say this is the simple document you have, and you have one term. So the TF of this term oysters in this document above would be equal to the count. of the number of times oysters occurs in this. So this is 3. Okay. Then there are other variants of TF. So other variants of computing TF. So there is TF not given a term and a document. This is the Boolean version of TF. It would be 1 if T occurs in D, otherwise 0. See? Then there is another variant called adjusted. TF. In that case, TF, let's call it TFA, given a term and a document. It's 1 plus ft of d that we computed earlier above, divided by the number of words in d. ठीक है? So in the above case, let me give it to you. For example, in this case, oysters would be 0, and in this case, the adjusted TF for oysters in this document would be 1 plus 3. So this is your F oysters in the document. So this is 3 divided by the total number of words in D, which is 1, 2, 3, 4, 5. See? So this is 4 over 5. So this is another way of computing term frequency. There are other variants as well, such as the log scaled TF. And in that TF, the log version is computed as the log of 1 plus FTD. Okay? This is log of 1 plus whatever the frequency you got from the raw term frequency. Okay? So that's TF, and that now brings us to document frequency. DF, right? So this is kind of the inverse of how we were looking at terms. So again, we have a number of documents and we have one term. Right? So this is the number of documents in which the term occurs. A given term occurs. See? So in that case, for example, let's say I have 3 documents, D1, D2, D3, and let me specify these documents. So let's say the first document says oysters eat seaweed. Okay? Then the other document has oysters eat oysters, and the last document has oysters eat small fish. Okay? So let's say there are 3 documents in our document collection. And we would like to find out document frequency of the word oysters. In that case, that would be 3. And if you wanted the document frequency of the word fish, because it occurs only in one document, the count of the number of documents in which this term occurs is 1. Okay? So now, how about the informativeness of a word? And how is that related to document frequency? Okay? The common terms, the common words or terms, I'm using these two interchangeably for now, that occur in many documents do very little or do not help in separating irrelevant documents. Right? So, for example, if you are searching for something, the word oysters in these documents is not really helping. Neither is the word eat, because they occur in all the documents. See? So, such terms should be weighted less. So, these common words and terms uh, should be weighted less, right? And the terms which appear very, very infrequently, such as in these documents, it's seaweed and fish in 3 documents, right? If the query contains somewhere fish, that means you can pinpoint to this document amongst these 3. This is the most relevant as compared to the other 2, right? So for that, we have something called inverse document frequency. And inverse because we are saying a term is rare and yet it is very important, and that's why we take the inverse, and it comes in very few documents. So this is a measure of how much information is contained in a term. Okay? And this is calculated using this formula of IDF. For IDF, you need a term and then you have a set of documents. It's computed by the negative log of nt divided by n. So this is this is the number of documents in which t occurs, and this is the total number of documents. ठीक है? So let me flesh it out. So D is basically the set of all documents, D1, D2, all the way to DM. And this N is essentially the size of this D, where N of T is equal to, so let's say this document in D and T is in this document, and the size of this, that is the number of documents in which this term T occurs, is N of T, just written formally. Right? So let me give you an example of how this works, or just an example in a list. So there are different terms. Let's say document frequency in which these terms occur, and IDF of this term in this document. Okay? So this is over a number of documents. So given different terms such as anthropocentric, uh, and let me give you some other terms. Animal, a very common term. Sunday, fly, under, and then let me give you an example of a stop word like the most common stop word is the. So document frequency, let's say we had a set of documents. This term only occurred in one document, right? Animal occurred in 100 documents, so 100 documents related to animals or just mentioning animals. Sunday occurred in 1000 documents. Fly occurred in 10,000 documents. Under occurred in 100,000 of these documents. The occurred in all the million documents that we were looking at. Okay? So the IDF, which would be the inverse, actually captures uh, the reverse order of magnitude. So IDF for anthropocentric turned out to be 6. For animal, it turned out to be 4. Sunday, it turned out to be 3. For fly, it turned out to be 2. And then under, a 1. And the most common term, which is the IDF, was close to 0. Not exactly 0, but it was very, very close to 0. So that's what IDF is. It gives the importance of the term with relation to a set of documents. Yeah. Now, that brings us to TF-IDF, a very common feature used to index documents and order them in the order of importance given particular terms. So this TF-IDF, as you can imagine, combines the notions of term frequency and inverse document frequency. Okay? So here we are getting frequent terms, and here we are getting important terms. Okay? So the way TF-IDF is computed, TF-IDF, it's written this way. You have a term, you have a particular document, then you have the entire set of documents. So you need to give a term, you need to give a particular document for which you are computing the TF-IDF, and you need to give it the entire set of documents. So first you compute TF, however you like. So TF requires the term and the document. Then you multiply it with IDF, which would require the term and the set of documents. So that's it. Uh, higher TF would mean it's a frequent term. Higher IDF would mean it's an important term. And if the importance goes down, the frequency of the term goes up, TF IDF goes down. Similarly, if TF is low, IDF is high, the TF IDF goes low. So it's a balance. So that means high TF IDF means what? It means a high TF in a given document and a high IDF overall in all D. See? So that means ke for that document, TF-IDF is very high. That document is extremely relevant for that particular terms. See? So this one of the advantages of TF-IDF is that TF-IDF automatically filters out common terms which are not really relevant. So you do not need to perform stop word removal for calculating for applying an analysis on a document given you have TF-IDF. Okay. So let's conclude with an example of the entire thing. And this is a short example. Let's say we have a set of documents D, and there are three documents: document 1, document 2, document 3. And these are not long documents. These are, somewhat like what you've seen before. So let's say jellyfish eats fish, fish eats small fish, and oysters eats fish. See? So now I've made oysters something of importance. Okay. So for document 1, you can see the count of these terms. So the word jelly appears once in document 1. Um, The word fish appears twice in document 1, and the word eats appears once in document 1. Similarly, in document 2, the count of words is for fish, eats, and small. That fish appears twice, eats appears once, small appears once. Same thing with document 3. Oysters eats fish. So they appear one time. The three words exactly in document 3. See? So let's say we are using adjusted TF for term document, and we can make a matrix of these things. But let's say, okay, I just want to figure out TF for the word fish in document 1. That would be 2/4. That's the total number of no adjusted. Let me look at it. How did I define adjusted TF? Okay, adjusted TF has a 1 added to the frequency. So I'll need to add a 1, and that would be, instead of 2/4, that would be 3/4. Right? So where are we? So TF for the word fish in document 2 would again be 3/4, and TF for fish in document 3 would be 2/3. Okay. Now, if I look at IDF for fish and all the documents, that would be the inverse log of the number of documents in which fish occurs over the total number of documents. That's 3. So that turns out to be 0. Similarly, in that case, if I'm computing TF-IDF of fish for any document uh, on this document set, that would turn out to be 0 because for all documents, IDF is 0. How about the word oysters? So TF for oysters in document 1, let's see, where is it? Oysters does not appear in document 1, so it's 1 by 4. TF adjusted for oysters. Document 2 does not appear, so that's 1 by 4. TF for oysters, document 3 would be 1. So there is oysters does occur, so that's 2 by 3. And if I take the IDF for oysters and all these documents D, that is the inverse log of the count of times oysters occurs, that's, or the count of documents in which oysters occurs, that's 1, and that's 3. So this turns out to be approximately 0.477. See? And for each one of these documents, the TF-IDF would be computed separately for oysters, D1, given the set of documents, that would be uh, TF, which is 1 by 4, multiplied by IDF, that's the minus log of, so that would be, in fact, this becomes log of 3, and this is 0.119. Similarly, TF IDF can be computed for document 2 for this set of documents. That would again be 1 by 4. And for the IDF is the same. So that's log 3. And then again, the value is the same. So TF IDF for oysters and document 3 for this document set is 2 by 3 multiplied by log 3, and you can figure out okay, this has a higher value such as 0.29 or something. Let me see, 0.477. Yep, so 0.27 probably. So you can calculate the actual value. So it's interesting to look at the theoretical justification of TF-IDF, and you can see from this example, okay, because the TF-IDF value for oysters is highest for these documents, so you can take an argmax over the TF-IDF and see that this is the document D3, which is most relevant in terms of oysters as compared to the remaining two documents. Okay, so thank you very much. That's it for what I have for today's lecture, and thank you.